Okay, so thanks, Trevor, for that lead in. I don't feel bad about not explaining all the math behind it. So I'm going to be talking about Python, the scientific Python ecosystem as a platform for the algebraic collective model, and obviously not just restricted to the algebraic collective model, but it's you should be considering it as a kind of a unifying platform for delivering scientific software. So acting up a little bit. So the title involves a couple of terms. It involves scientific Python, involves the algebraic collective model. And you know, the way I think of the significance of the algebraic collective model is that it's clever math behind physical theory that extends the range of physical systems that a computer can handle. And historically, if you look at the various kinds of software that's been involved in nuclear physics or physics in general, there's been a variety of languages. Like I've personally used Fortran, I've used APL with David. 1 year, he gave me a Pascal program and I had to convert it to something or I had to get it running. And then, of course, in the literature, you see C, C++, and then more recently, the computer algebra systems like Mathematica, Maple, linear algebra systems like MATLAB, et cetera. So there's a lot of different technologies. But what's happened recently is the internet has generated a ton of data. We didn't have that much data 30 years ago, but there's been a lot of data, and it's given people an opportunity to mine the data, extract value from the data, and for economic reasons. And this has caused the development of software and hardware to process it. And in that development, Python has emerged as the dominant platform. It's really the main platform right now used in data science and machine learning. But in addition, it's got a rich set of scientific capabilities that make it well suited for physics. And what I'd like to do is tell you my experience about porting or converting the Welsh Rowe ACM code that Trevor alluded to, and I think most of you are familiar with. The implementation was Maple, and I converted it to Python just to sort of to see how it would do, see whether Python was up to it. And so my conclusion is it was up to it. And I'm going to argue that Python is very appropriate for this type of calculation. And it has many advantages, both engineering and economic, over special purpose computer algebra systems. So I'm going to talk a bit about the background, why I got into this. Talk a bit about the algebraic collective model, and I'm not really going to go into the deep physics. I kind of wanted to explain to David's family and friends who may want to kind of a high level understanding of what it is. And then I'll talk about the Python ecosystem, and then I'll discuss what I'm going to do next and wrap it up. So this is very sensitive. Oop. Okay. So I met David in 1977, and we were at a conference, and in Tübingen, actually, a math physics conference, and I was standing in line at a buffet, and we started talking, and George Rosenstiel was there, and all I remember is that we got into some very technical discussion about Hilbert spaces, and then I didn't hear from Dave for a couple of years. I was doing computational atomic physics at the time. And then he contacted me about a year later, and it turned out that Helen Friedhoff, who Peter Turner mentioned, I guess she was on sabbatical at the University of Toronto. She was one of my professors at York University, where I did my bachelor degree. And he contacted me and offered me a postdoc, which I took. But I only was a postdoc for about a year, and then I went into industry and I became a software engineer, which I've done for 41 years. But during that time, I became a family friend of David, and Una's wonderful, and got to know Amanda, who's a very talented artist. But with David, we would talk math, physics, and computing. We also played squash and badminton. I would beat him at squash, he would beat me at badminton. It's a good arrangement. And we ate a lot of sushi and drank a lot of scotch. Then in 2019, I invited his family over for a barbecue. And David was telling me about this wonderful ACM code. He was very proud of it, but he was kind of disappointed. He said, it's this great model, but it's not getting the amount of adoption. And I said, oh, have you heard about Python? So I was looking for a way to get back into physics problems, and decided, I volunteered to do the conversion. So the next day, David sent me a note, and he's talking about the ACM model, the code. And he said that when he was worried about Maple, he said, he was hoping that the model would be widely adopted, but he said the use of Maple, I am assuming, to be the obstacle that is happening. So he felt that because it was written in Maple, which is a proprietary system, it wasn't being adopted. And he also said that when he submitted the article, to Computer Physics Communication, the editor said the language you've chosen might be a barrier to adoption. So that was the background. So I was motivated to do it. So that was 2019. And of course, I didn't do it for several years. I kind of made a start at it, but I didn't really make much progress. But then, unfortunately, David died. And we started talking about this memorial event. And finally, around March, it seemed like we locked in a date. It seemed like the pandemic was clear and we could actually hold it. So I thought, oh, well, I've got 3 months left. I better get my head down and do it. And it took me about 6 weeks to convert the code. It was, it's fairly complex code, but did get it done. Okay, so now I'd like to just explain a bit about collective motion. I'm sure everybody here understands what collective motion is, but we don't see collective motion just in nucleus. It's actually it occurs in many other contexts. For example, schools of fish, or murmurations of starlings. Perhaps you've seen them; they're quite amazing. And obviously, protons and neutrons in the nucleus also behave collectively, and this resulted in a Nobel Prize for Bohr, Modelson, and Rainwater. So here's a picture of fish. Obviously, the fish aren't banging into each other; they're moving in a uniform way, a coordinated way. Yet each fish, there's no head fish telling all the other fish what to do. It's just a result of their interactions. And here's a murmuration of starlings. And if you go on the web, you'll see a lot of these pictures. They're quite interesting, quite striking. So these are examples of collective motion. Okay, so what about algebraic models? This is very finicky for some reason. Okay, algebraic models. So when you learn physics, you're normally taught quantum mechanics in terms of the Schrodinger equation, which is a differential equation. So in system, you could up Schrodinger equation for it. And most differentials are kind of hard to solve. Some have simple solutions. But in principle, any differential equation can be solved with a sufficiently powerful computer. However, it turns out that when you full solution, some untrue. So, when you go through the textbooks, you see the simple models. The reason you get a simple answer is because there's usually some underlying symmetry. For example, a three-dimensional system may have rotational symmetry, which simplifies things. Now, if there is an underlying symmetry, the differential equation can be expressed in terms of the group operators, and you can kind of magically find the solution without solving the differential equation. Probably the most well-known example of this is the harmonic oscillator. It's just a, in the one-dimensional case, a weight on a spring. In this case, the underlying symmetry is a symplectic group. Now, if we look at an atomic nucleus, it's composed of big N nucleons, protons and neutrons. For example, for uranium-235, there would be 235 nucleons. Now, each nucleon is described by 3 coordinates. So you have 3n coordinates, and no conceivable classical computer could ever solve Schrodinger's equations pragmatically. Theoretically, if you have an infinitely big computer, it could. Pragmatically, you can't. I mean, this is way beyond any classical computer to solve. It's conceivable that some future quantum computer might be able to solve it. Kind of interesting that Peter Turner was talking about quantum supremacy. Obviously, a nucleus knows how to compute itself. So it may be that a quantum computer could do these things. Okay, so this is where the algebraic collective model comes in. Rather than having 3n coordinates, you could have like 500 or 600 coordinates for a big nucleus, it dramatically reduces it to 5. And these 5 are the components of the quadrupole moment tensor. So now you get to something which is more tractable. And in addition, there is underlying symmetry. There's the SO5 symmetry, which Trevor talked about. And that deals with roughly the orientation of the quadrupole moment. And then the SU11 symmetry, which deals with the magnitude of quadrupole moment. So what's a quadrupole moment? So if you think of this swarm of nucleons, you could imagine them as being a continuous mass distribution. The quadrupole moment is a measure of how much this distribution differs from a perfectly spherically symmetric distribution. There are 5 independent components, but if you rotate the positions of the nucleons, that induces a rotation of the quadrupole moment. And since there are 5 components, that's where you get SO5. Now, it turns out that what's called the quadrupole moment in physics is actually very similar to what a statistician would call the covariance of a data set. And also, if you do finance, if you play the stock market, you'll know what the beta of a stock of an asset is. It's the volatility of an asset. And they're basically the same thing mathematically. So you think of the quadrupole moment as some statistical measure on this distribution of mass. And by coincidence, I don't know if it is a coincidence, but the AZM also calls that thing beta. So I don't know if the guys who coined the term beta in finance were physicists. Okay, now the Welsh Rowe code. So this was put online in 2015, published in the Computer Physics Communications in 2016. It's 5,571 lines of highly commented Maple source code. In addition, and thank you for the comments, Trevor. In addition, there are pre-computed data files. So as Trevor talked about before, he's working on the more algebraic way of computing these things, but there were apparently it was thought that it was time intensive to calculate things, so these were pre-computed. So it turns out that trade-offs, now this is a bit of a tangent, but it turns out that there's trade-offs now between computation and reading data off a disk. And it may be that it's actually just faster to compute it on the fly now. Of course, you'd cache it, but so it would be an interesting exercise to clock how fast it is actually to compute these things, because it's a little bit of annoying. It's an annoying setup detail that you have to install these pre-computed files now. In any case, there's also a very extensive Maple worksheet with lots of examples of how to use the code. And a user can cook up a fairly general Hamiltonian, and then find the energy levels and the states, and then compute transition amplitudes and rates between these states. So that's what the code does. Okay, I actually have the code running live on my laptop, but I won't go into a demo right now. If I have a bit time later and you're interested, I'll show the code running. But you can't see it, but I'm just going to focus on elapsed time. So this little calculation took 9 seconds on my desktop computer. And I put this code, the code on GitHub. So I swear by GitHub. You'll go crazy maintaining versions of code if you don't use a version control system. So the code is there, and I've actually opened a few little issues, questions I had about the code, which I would love Trevor to respond to if he ever gets a GitHub ID, but maybe we can persuade him to do that. So, but the code was pretty clear. I didn't really find much questionable about it. Okay, now I've done a similar, I've ported the code and I've recreated the worksheet to some degree. I haven't gone through the whole thing, but this is an image of what's called a Jupyter notebook, which is the Python version of a Maple worksheet or a Mathematica notebook. So it looks very similar. And down here, I just probably can't read it, but that says 3 seconds. So in fact, the Python code is now running faster, and I haven't really even optimized it much. And I've also created a GitHub repository, so anybody can grab the code. I mean, I'm not finished. I have to finish testing first, so I'm not really pushing it at the moment. But if you want it, you can find it. Okay, so now let's talk about Python. So Python is actually pretty well designed. It's a fairly modern language, a very clean language. It's what's called dynamically typed. So in a language like Java or C#, you declare the types of variables. You can never change the type at runtime. Python is actually strongly typed, but the type of the variable can change at runtime, which makes it a little more productive, a little faster to get stuff going. It's also object-oriented, which means you can package code, you can do what's called information hiding. It's a way of composing small pieces into larger systems. And by contrast, Maple is not really object-oriented. If you try hard, you can kind of do objects, but object orientation is a well-known good practice in software development. And it's also got a lot of functional programming features, which means that functions themselves are objects, so you can pass functions around. Now, it's interpreted, i.e. not compiled. However, all the performance critical things call highly tuned libraries that coded in C or could be external languages. It reuses existing libraries like LAPACK, which also Maple does. So people tend to reuse the well-worn, well-tested code. In addition, Python has very high-level mathematical. For example, it does exact integer arithmetic. It has high-precision real and complex numbers built in. And it also has mathematical data structures like sets, lists, tuples, and maps, which the Python people call dictionaries. Another important thing about Python, it's free and open source. It's governed by the Python Software Foundation. It's got a huge collection of third-party packages, and I'll talk about some of these in detail. It's also got a very good package manager, a place where you can upload your code and anybody else can download it. It's called the Python Package Index. And there are many excellent integrated development environments for Python, which is an advantage, comparing it to what Maple provides. these integrated development environments are very good. And I use one called PyCharm by JetBrains. There's a free version of that. I'll talk about that a little bit. Okay, so this is just a shot of the main Python site, and information about the Python Software Foundation. So this is the group who govern Python. Couple of packages that I like. One is called mypy. So as I mentioned, Python is not, it's dynamically typed, but you can put what are called type hints or type annotations in your code, which is a big advantage. It's a way of documenting the code, and you can also do a kind of lint for type checking on the code. So I recommend that highly. Another thing very important for software development is automated testing. So Trevor provided a lot of test cases, but you have to run them manually. Whereas in Python, there's a very easy to use framework for creating test cases, which you can just run automatically. And typically what you do is you make changes to the code, you run your test suite. So my test suite is over 600 test cases right now. It runs in 9 seconds. So it's a very, very good way of catching regressions in your code as you're developing. This is the Python package index. And I just want to point out these numbers. So there's 378,000 projects. Of course, most of them are, crap, but there's there's thousands and thousands of really great ones, and almost 600,000 users. So people are contributing to this. They're downloading code from it. So this is a huge thing. Every popular programming language has something like this. So it's a way of sharing code very, very easily. And this is just a screenshot of PyCharm. So you can get a professional version that you pay money for, or you can get a community edition, which is free. And there are many other very good Python development environments. Okay, so by the way, this presentation is actually a Jupyter notebook. So this is the first time I've used it to generate a presentation. So it's a little finicky here, but okay. So what is the scientific Python ecosystem? Well, it's really a set of technologies, and I'll just go through them quickly. So mpmath, this is this means multiple precision math. So you can do arbitrary precision floating point arithmetic, and it's all optimized. And matplotlib, I think I know what's the problem. I'm hovering over the arrow. It's triggering it. Okay, matplotlib. This is a very extensive and easy to use plotting library. Which provides the same features that MATLAB has for plotting. And there are also other very good plotting libraries. Okay, then NumPy. So NumPy you can think of as n-dimensional arrays, so matrices, tensors, whatever, vectors, and it implements vectorized operations. So when you're, and this is where the speed comes from. So if you have 2 vectors of a million elements, if you wrote it as a Python loop, you'd be indexing each element and adding them, and it would take a long time. It would take like 100 times longer than it should. If you call NumPy, you just say a plus b, and it will go into the low-level C code and just apply that operation in parallel. And in fact, if you're running on a platform that has multiple cores or multiple processors or whatever, it will, you'll have a certain back end to optimize that. So NumPy is very, very fast. So it should be used for any kind of numerical array processing. Pandas is really the thing that Pandas gives you is the concept of a data frame, which you can think of as being a relational database table. Or you think of it like an Excel spreadsheet, but it has columns. Each column can be of a different data type. And again, it's built on top of NumPy, and it does fast vectorized operations. It does statistics. And it's also got a very simple interface to matplotlib. And it's extensively used in the data science community. Okay, and then Jupyter, this is the notebook technology. And in fact, it's Jupyter is not strictly Python. It started out as being Python only. It was called IPython. Apparently, Jupyter is short for Julia, Python, and R. So in the data science world, R is very popular. Julia is sort of a newer language, modern language focused on numerical analysis. So you can have multiple backends. In fact, there's around, I don't know, there's probably 100 so-called kernels. So you can embed any kind of executable code you want in a notebook. There's probably one for Maple. Okay, SciPy. SciPy has a lot of mathematical special function calculations, very efficient. It also, it's also set up to do these vectorized operations on them. And then it has specialized libraries for things like machine learning. And then SciPy, this is the symbolic library, which is roughly, it's very, very similar to Maple. When I was doing the conversion from Maple, there would almost be like a word for word. They often use the same word for the same function. In addition, there are distributions of Python. So if you're just an end user, if you're not really going to do heavy-duty programming, but you just want something to do interactive work with, then there's a couple. SageMath, which directly goes after the Maple Mathematica space. So it's a fairly big distribution. And then there's Anaconda, which packages all the scientific Python stuff, plus other things like R and various other tools. So those are kind of an easy install. They're not really what you'd use if you're developing code, though. But if you just want to use it, you would use one of these distributions. And this is the SageMath site, and here's the Anaconda site. Okay, so let's talk a bit more about Jupyter. So as I mentioned, it started out as pure Python, and then it got generalized, so you could plug in arbitrary backends. And in fact, there's a whole page of kernels. So the odds are, if you have a favorite technology, you can plug it into a Jupyter notebook. JupyterLab is an interactive development environment. So it's like it's a web-based development environment. So you don't have to install anything. You just run it through your browser. And Jupyter Hub is a place where you can host Jupyter notebooks, and do collaboration. But in addition, there's several other websites that are now hosting Jupyter notebooks. So, once you publish your stuff, and this is what I intend to do, once, the code is ready for humans, I will put the workbooks up on a public site and, provide links to them so people can just go there and, enter their model, get do the calculations. So this is what JupyterLab looks like. It's, it's like it is an integrated development environment, but it's all web-based. And this is the Jupyter Hub site. And then here are the various other places where you can host Jupyter notebooks. So this one, Binder, if you have a project that contains Jupyter notebooks running in GitHub, you can just point Binder at it and it will let you run the notebook. So you don't have to install anything. It's all web-based. Kaggle is another similar site. Okay, Google Colab. So this is an interesting one. They're really going after the machine learning people, and you can get a very powerful compute engine in the back, backing up your notebook, potentially using GPUs. And CoCal, yet another place to host notebooks. And the company I mentioned before, JetBrains, that does the PyCharm IDE, also is now hosting Jupyter notebooks at a site called Datalore. So, so the message here is you don't have to set up any infrastructure. If you create a notebook and you want people to, look at it or use it, you just put it on one of these sites. And I know that there are some academic technologies too. Some universities are doing this. They're setting up their own Jupyter Notebook servers. Okay, so my experience converting the Maple to Python. So to begin with, Maple and Python are actually very similar as languages. They're both high level, they're mathematical, they're interpreted. The initial conversion was very direct. And I made extensive use of SciPy, the symbolic library. So all the calculations were done symbolically because I could get the code running very quickly and compare it to the Maple output. However, the code is actually, the ACM code is actually a mixture of symbolic and numeric processing. And I wanted to ask Trevor, like, where he thought the dividing line was. It's nice to get mathematically perfect expressions involving square roots, etc., to see what it is. But if all you're doing is, diagonalizing a matrix, you've got to convert that to a floating point number anyway. And you probably get a factor of 100 speed up if you don't do it symbolically. So the question is, why do, there's some places where you should do it symbolically, but where's that dividing line? In software development, we have to understand the requirements, right? If the requirement is to produce numeric results, then you want it to go fast because somebody's sitting at their notebook waiting for an answer. So you want it to go fast. But if you want exact mathematical results, that's a different problem. So, and maybe we actually have two code bases. Maybe we have functions written in symbolic expressions and then optimized functions. But then we can actually use the symbolic stuff as a check on the numeric stuff. At any rate, so it was very slow. But one of the good things about modern programming languages and development environments is that you can do things like profile the execution. So you can see where is the time being spent. I did that, and of course, it was being spent in SciPy functions. So I looked at the worst cases, where's the biggest bang for your buck, and converted a lot of the matrix stuff to NumPy. But I didn't do it everywhere. I just did enough to get the code running faster. And right now, the code is around 3 times faster than the Maple code, and it could go even faster if I make use of these vectorized expressions. Instead of writing loops, I converted to high-level NumPy arrays and do array operations on them. I think it could go a lot faster, which is a good thing if you're sitting at a terminal, if you're sitting at your keyboard waiting for an answer. I did find some problems. You run the code and your test case fails. So one of them I traced to the meaning of what is the binomial coefficient of -1, -1. I'm going to do a poll here. Would anybody venture, Joe or Trevor, you're mathematicians, what do you think that should be? Did you say 1? You said 1? What do you say? What? You'd say 0. You'd say, he's right. You call yourself a mathematician? Okay, so Maple got it right. Maple returns 1. And Maple gives if you look at their documentation, they give a very good explanation of how, what it means for these negative integers. So I checked the SciPy code and they said, as a matter of convenience, we're going to return 0 for negative values. Okay, so I opened an issue. So the good thing about open source is you can open an issue, you can argue with them, and you can even submit a fix if you have that much energy. And then another case was the equation solver. It's actually finding a numerical root, but it's trying to do it symbolically, and it just failed. There's no algorithm for symbolically solving equations. You can't solve them numerically. So I just, I used a SciPy root finder. But just to, what did I do? Okay. There we go. But as I mentioned, you know, the good thing about these projects is they're open source. So most of them are hosted on GitHub, and I opened an issue, and there's a bit of a discussion. And you know, of course, whenever you find a bug, they'll say, well, you know, we're a little nervous about fixing it because some people might be depending on that behavior, and is it really the correct mathematical definition, etc. But at any rate, when I have the energy, I'll push it more. But I did get a very immediate response, so that's good. It's a very active repository. So, you know, you can if you look at the change history. So, like the most recent one is 3 days ago. You know, so it's a very active code base, and you know they're looking for contributions. So it may be that parts of this should be contributed back into the SciPy code base. Maybe the stuff you're working on would be a good fit for that. Okay, so what are the advantages? So first of all, Python is a well-designed modern programming language. It has excellent development environments, great tools for debugging, testing, execution profiling, supports object-oriented design, which is very useful for scaling up code. It has the PyPy infrastructure for publishing code. It's free and open source. No license fees. You can fix bugs, add enhancements, etc. And it, you know, future-proofs your code. Like, you're not going to worry about Python going broke. It's not going to go broke. It has too much momentum. Too many people rely on it. And it also has a very large developer base. So if you're looking for students to work on your research projects, they probably learned Python, or they probably either learned it in school, or they just learned it as a hobby because it's a cool thing to do. So you're going to get a skill base, and then, you know, they may not want to go into physics after they graduate. They can go into industry, and if they have Python skills, they're going to have more opportunity. So just as a data point, there are many surveys on programming language popularity. So this one, Stack Overflow, does an annual survey. They just ask lots of programmers. So 80,000 developers responded. Big, you know, that's a big sample. And they say, which programming, scripting, and markup language have you done extensive development work in over the past year, and which do you want to work in over the next year? Okay, so at number 3, 48% said Python. At number 23, 4.6% said MATLAB. Maple and Mathematica were not even, were not significant enough to be recorded. I will show you that. You're a good straight man. You know what they say when you're doing a presentation? You say that's a good question versus that's a great question. Great question is one that you have a slide for. So I have a slide for that. That's a great question. So this is the chart. I mean, you can, Stack Overflow programming survey, go Google it. So number 1 was JavaScript. So why JavaScript? Well, obviously for web pages. Most modern web user interfaces are written in JavaScript. You would not want to do scientific software in JavaScript. Okay, it's good for scripting web pages. Number 2, HTML and CSS. Obviously, web pages, right? You're not going to do scientific programming in well, maybe you'll do a user interface in them, but the code is not going to be written in. They're not programming languages; they're markup languages. So number 3, like okay, JavaScript is a real programming language. And in fact, you can do server-side programming using a technology called Node.js. So a lot of people like JavaScript because it's, you learn one language, you have the back end and the front end in the same language. So that's attractive. But the number 3 programming language is Python. And then if you go down the list, let's see. Well, SQL, which is a query language, not a general purpose programming language, is number 4. Java, number 5. And then you get the usual suspects. And bottom rank, well, they made the top, right? They're still good programming languages, but I encourage you to go to this web page. Okay, so MATLAB is here at 4.6%. Julia is 1.3%. No Mathematica, no Maple, no Fortran in that list. Okay. Okay, next. So I'm going to say I have a version 1.0 release after I've reproduced all the results in Trevor's Maple worksheet. So, right now I'm up to like section 4.5. So when it's reproduced the results and I've tested it, I'm sure it's correct, I will release it and I'll try to get feedback. So I don't know who among this group would be interested in using it, but I will certainly look at the people who've cited the Maple version and try to get their input on the on this Python version. Okay, and if I get positive feedback, I'll go on to version 2, and I will convert all the numeric code to using vectorized functions, which I think will give it another at least factor of 10 speed up. And I'm going to go through and refactor the code to make it more object oriented, so to take care of the packaging. Because, Trevor, okay, you're a mathematician, you're not a software engineer, but it's like 5,500 lines of Maple code in one file. It's hard to understand all that. You have to break it up into classes, with clean APIs, etc. So if you want people to build on it, you have to kind of engineer it so that it's more consumable. You did, and you know what I did? I took those sections and I put them in separate files, just for my own sanity, because you can't edit it's not good to edit a 5,500 line file. So I'm impressed you did it. I'm impressed you could get it going. Now, in order to put something out there, like especially to NumPy, you also have to have documentation. And there's it's kind of like JavaDoc, if you know what that is. You put documentation in the source code using a certain markup. It's called Sphinx in Python. So in order to get anything accepted, it has to meet their documentation standards. And maybe pull it apart a bit, like what's the more pure mathematical part, like the SO5 stuff might be a good thing, but pull it out, into smaller pieces that stand alone and make those possibly as contributions to SciPy. Definitely publish the code on PyPy so people can easily get it. And then write up an article on this effort and submit it to Computer Physics Communications. Okay, so now this is a little kind of off topic, maybe, but doing this, it struck me that, and I'm not the first one to observe this, but it seems like if you look at typical scientific paper, it kind of it refers to old papers, but it also reproduces a lot of results to make it more self-contained. And certainly, when you're developing code, if you're changing languages, you can't easily reuse code in a different language. You often have to port it, and so it's a lot of reinventing the wheel in a sense, and it's not how the software industry works. And what if a scientific paper was more than just informal mathematics? Like we saw today, like you showed some math. I'm sure anybody who showed any math, I bet the math is wrong. There's a sign error or whatever, or a factor of 2 out. Or an operator should have been squared and it's not, you make a lot of errors when you write math because there's really no way to check it other than a human reviewing it. But in the software industry, there's actually higher level languages that are called formal specification languages, where you can say, this is what this is what should be computed. And they're not terribly widespread. They're used, say, in safety critical systems. I have personally used them. They allow some level of type checking, model checking. So it's not just for humans. It's a computer can understand it because you're describing the math in a formal language. I like one called Z notation, which was developed in Europe. I've used it. Actually, I used it on a W3 specification. And going even further, when you show a derivation in your paper, how do you know it's right? How do you know you didn't make an error? Well, right now there are proof checkers. So if you take the first step and you write things formally, you can actually create a machine checkable proof. Now, I'm a bit skeptical of machines finding proofs. I think humans are still better at that. But if you go to the trouble of formalizing your proof, at least a computer can check it. And one that's getting a lot of attention now is called the lean theorem prover. And it's being used by some very reputable mathematicians to formalize math and to check proofs. Of course, you need a bit of infrastructure there, because there's a lot of mathematical definitions that first have to be formalized before you can get to the more advanced stuff. Okay, so why bother doing that? So I think the making papers a little more computer friendly gives you the advantage that you can you can use things which the software industry has been using. For example, reuse of results. You can just, if you're convinced that definitions are correct, that proofs are correct, you can just kind of reference them and build on them. Also, if you're using a formal language, that lets documents be indexed and therefore searched, so you can find results. And hopefully the result would be that the quality of the software would be better, would be more correct. So I'm kind of interested in doing that. I think the ACM code would be a good, it's a realistic test case, whether it could be done for it. So in conclusion, I would argue that Python is now a viable alternative to the traditional special purpose computer algebra systems. Python's being used every day on very large scale tasks. It has language features which make it better for developing large complex applications. It's free and open source, which means your code will be future proof, and it has a very large and active developer community. Python skills are in high demand by industry, so therefore any grad students you produce will have better prospects if they want to leave physics. And by standardizing on Python, it would be more easy to build on past work, the way the software industry does. And a couple of references. So the paper by Trevor and David on the code. I've also included a very good article. One of the authors was a creator of the IPython, which is now called the Jupyter platform. And it's a very well thought out argument for why Python should be used. And notice the date on that is 2011. So we're only 10 years behind. But some people were pushing this 10 years ago. And if it was good 10 years ago, it's even better today. All right. And it is. It's a lot more mature. So that's it for me. Be happy to take any questions, probably running over a bit.
Hi, Arthur.
Yeah.
This is Carol.
Hi, Carol.
When you upload or specify this SciMPy, as the author of that package, are you able to monitor, or in the future you're able to monitor how many people, the traffic for that package?
Yeah. Yeah. No, absolutely. The downloads are tracked. And then people can also rate your software. They can give you stars and likes, depending on the platform. So there's a mechanism at GitHub. There's a mechanism at PyPy.
Mm-hmm.
Yeah. So plus it gives you a way to interact with the user. So they don't, they could be anonymous, but if they want to talk with, if they want to reach you, they know how to reach you. Yeah.
Great.
So that's the norm in software. And it, I think it has a lot to recommend it. Anything else? Trevor.
You mentioned
yeah. Yeah. No, it ran in 9. the example I used, that was just the first example. So let me tell you, the first time I ran it, Python took 80 seconds. And I thought, I better tune this. So then I tuned it and it ran 3 times faster.
What is faster now? It doesn't come to American. Was it only one by nations?
Well, I think it must be, yeah, so this was the piece of code. We're just diagonalizing a very simple Hamiltonian. So where the speed up was, I think possibly the NumPy library is more efficient than whatever Maple was using to do vectorized addition. But you see but you're right, the underlying numerical analysis, I believe they're both using LAPACK under the covers. So it's kind of the wrapping, you know, before you get to that. Oh, it's very tiny. It's, well, I'd be happy to give you a demo later, but I'd probably blown my time flat quite badly. Maybe at a coffee break, I'll run the code for you. Yeah.
Software Maple and just use it. Actually, as a matter of fact, they don't talk about the Python, they talk about Jupyter. Professor, this is in Jupyter. I got this result. And but also it's sometimes, I mean, it's young.
It's not that young. but you see the amount of attention a code gets is based on how many people are using it. And you kind of vote with your feet, you know, if something's not working, you want it to work better, you put in the effort to improve it.
It reminds me a lot of like the Maple that I used in undergrad, that I found was fantastic. In the Maple 3,
yeah.
Especially it's been at the same stage right now. You may or may not agree with that. There's a lot of enthusiasm associated with that.
With what? SciPy.
Well, I see a lot of packages. Website,
yeah.
Put together or people like yourself to design something for a particular purpose. So,
okay, so let me be clear. Like Maple, Mathematica, MATLAB, they're all great. If they're good, if you want to do interactive work. If you want to build software that other people build on, I think you should use a language like, well, I think you should use Python. As, you know, to build up this, you know, code base of reusable code. Yeah. So they're all great, but you know, they're good for interactive use. They're not, in my opinion, they're not good as a basis for building up a software stack. I'm sorry, did I cut you off? Was there something else?
Well, like the same thing that I know people doing the algebra. Like this found things on algebra, but then again, that is all.
Well, that's it. Do you really want to do it symbolically, or is it a matrix of floats? You know, like, so you have to understand where's that sweet spot between doing things symbolically versus doing things numerically. You may want to do it symbolically if that gives you an accuracy edge, because maybe you get certain cancellations. So you want to simplify the expression first, then evaluate it. It may give you a more accurate result. But I don't, you know, for the particular case of the ACM code, I didn't see it as actually getting more accuracy. In fact, you know, we're getting like 8 digits accuracy. So, and you can always, you know, it's a bit of an art to writing code. You have to, you know, I mean, there's classic examples of how to write bad numerical code and good numerical code. You know, you can write it in a stable way or an unstable way. So it's a bit of an art. It's programming. But you don't, but the beauty of Mathematica and Maple is you don't have to think about it. You just write it symbolically and you hope that the system can figure it out, can simplify it. So it's very productive that way. Okay, so